Hi, this is EVE Project 3 with Alex.
Ellie.
And pantry.
So, for a little background, our project is on an aquaponics system where we want to measure the temperature and send a signal to heaters to turn on or off. In that project, we had this design where we would gather data with a soldered waterproof digital temp sensor from two similar fish tanks. Then we doubled down and create a system model to demonstrate this heating procedure. Okay, so we moved on to our mockup. There it is. Next, we started to CAD it. Luckily, Arduinos are very uniform, so we could add some pegs that fit the mounting holes. And we also added some slots for the cable and SD card, as well as our temperature sensor to go out the back. We ended up with a gorgeous product like this, and we added some tape to it so it could be wall mounted on any surface. Some pros and cons of this case is that it fits really snugly in its case. It allows access to all the ports. It can be mounted on pretty much any surface. Also, and the only con is that it's not waterproof, which we would like to see in an aquaponics system.
Paper model. Materials can affect the temperature of the aquarium. Wood, concrete, acrylic, glass have varying degrees of insulation properties. This has the potential to dampen the second relationship between room temperature and water temperature. Our example uses 70 degrees room temperature, meaning that the aquarium will try to reach equilibrium there. Water volume also plays a big role in how fast or slow the aquarium is heated or cooled, leading to heaters and chillers, which are the only practical controllable variable we have to set a specific temperature. Many fish species require specific temperature parameters that cannot stray more than a few degrees, making the sensor and correction vital to their habitat. The hypothesis was correct, but the heater represented a far more linear trend than previously expected, implying that the other factors made less of a difference in such a controlled setting. To collect data, we used our temperature probe while heating the aquarium. Using the probe, we were able to assess after some time when to turn off the heater. We first gathered a control graph of 70 degrees Fahrenheit. The second graph, we heated the big tank, 75 gallons, with a 300-watt heater. The third graph is a small tank with 40 gallons heated by a 150-watt heater, followed then by a comprehensive long test of heating the small tank with a 150-watt heater, then finally the small tank again, but with both heaters consisting of 450 watts. What we are playing with here is time, volume, and heating by wattage. What we have discovered is though all the graphs are linear, the relationship between heating and the volume are not directly proportional. Our sensors demonstrated this very well, and we allowed us to regulate the temperatures based on our 23 degrees Celsius desired temperatures. What didn't work so well is that the heating probe is not exact and is more stepwise.
Okay, so as you can see here are the 5 handmade linear regressions. You can see the equations in the bottom right. They're pretty close with what I'm going to show you next. So let's go through a speed run. All of these models are linear. All of these have pretty constant variances. The error terms are independent, and they're pretty normally distributed. Control, completely flat, no slope at all. R squared of 1. Residuals and best fit line are completely flat. Small tank. We can see our residuals are stagnated, still have the staircase effect. Our fit line is perfect, and our R squared is above 0.95. Large tank. Really weird fit line because our residuals are really affected by the stagnating effect, and we have a really low R squared. 150 watt heater. Again, perfect fit line, really high R squared. We still see a staircase effect in the residual plot, but this time they're more consistent and look better. And for the 450, we have a much thicker slope on our best fit line, which is still perfect. Really good R squared value. And for our variable, we still have the staircase effect, but it is a linear representation. in all graphs except the control and big tank, we have really high R-squared values. And for all of the graphs, we have really good trend lines, really good line fit plots, and really good residual plots, with a caveat that I'll get to later. What surprised me? Nothing much. Kind of expected that heater's going to make things hotter. Interesting new data. This is where we get to the R-squared values. So because of the precision of these temp sensors, you only get a change above 0.06 of a degree, and therefore that's why you get the staircase effect in all the graphs. And was it realistic? Besides the staircase effect, yeah, it's very realistic. Because you expect a heater to keep going until it reaches a certain temperature and then level off until it needs to be heated again.
This is a model made in AnyLogic that shows how heaters and chillers in a fish tank affect the temperature of the tank. The temperature is also affected by gallons of water flow inside the tank, lighting, if there is a lid or not, and room temperature. The heaters and coolers both started with initial values of 0. The first one models a situation where the heater and cooler are both on, but the heater is slightly stronger than the cooler, causing the overall temperature in the fish tank to rise. The second one models the heater and cooler being of equal strength, and the third one models the cooler being stronger than the heater. The equation shows that you start with room temperature and add or subtract based on the correlation of the parameter. I think these models are accurate because they show what you would expect.
We learned that the system is actually a smaller subsystem that can be implemented in an aquaponics greenhouse system, and that it can be a useful tool for us to monitor temperature.
This project made us apply all the concepts we learned throughout the semester. It allowed us to see how parts come together to make a working system, and this class taught us a holistic approach to viewing the world through a collection of parts that make up a system.
Everything went smoothly, except for a little hiccup with the position of our temp sensor.
Our two main challenges were soldering and a non-functioning data shield. Now, for soldering, it was easy. We just resoldered. But for the data shield, we decided that it would be best to just connect it to the laptop.
My favorite part of this course has been learning about the interconnectedness of the world. My favorite part of this project was collecting the data from the fish tanks, and my least favorite part was coding in AnyLogic.
Favorite part of this project, and funny enough, the course, is the hands-on learning experience that I don't get in other courses.